Hello, everybody. My name is Murray Shanahan, and I'm a professor of cognitive robotics at Imperial College London. And as of about 6 months ago, I also work part-time at DeepMind, Google DeepMind. And I'm here today to talk to you about artificial intelligence and a little bit about the future of artificial intelligence and the present artificial intelligence in the present day as well. So first of all, artificial intelligence today. Well, I'm going to start off by defining AI, defining artificial intelligence for you. So we might say that artificial intelligence is the construction of computers and robots that can carry out tasks that are normally thought to require intelligence when human beings carry them out. Well, now this, of course, is a bit of a circular definition. So it begs the question, what is intelligence? So a good definition of intelligence, one that I like, is along these lines, that intelligence is the ability to achieve goals and to make good decisions in a wide variety of environments. And it's that variety that's really is key to general intelligence. But most artificial intelligence work today concerns specialized applications. So, for example, playing chess, or self-driving cars, or medical diagnosis, or labeling the pictures in your photo album. So these are all specialized applications of artificial intelligence. Or otherwise, as a field of study, as an academic field or a scientific field, it concerns all of the bits and pieces of technology that contribute to those kinds of applications. So, for example, understanding computer vision, or language, or learning. Well, there is a great deal of excitement about artificial intelligence at the moment, and there's a great deal of expectation about its potential economic impact. And there have been a number of recent reports that have tried to quantify the economic impact that AI technology will have over the next, say, 10 years. And this is one report by Accenture, where they reckon that the annual economic growth in many Western countries is going to be in many cases double what it would have been without artificial intelligence, thanks to AI technology. And in China, there was recently this announcement by the China State Council of an initiative to try to make China one of the leading innovators and one of the leading powers in artificial intelligence over the next few decades, so by 2030. And as far as economic impact is concerned, well, here's another report. This one is by PricewaterhouseCoopers. It was published just this year, PwC. And in this report, they reckon that the contribution to the gross domestic product artificial intelligence technology is going to make over the next few decades is going to be really very considerable. So there's lots of expectation for what the economic impact of AI technology is going to be. Now I'm going to talk a little bit about the progress that we've made in AI and why it's exciting right now. Well, let's go back a little bit in history. So back in I'm really just going to talk about two landmarks in AI. One of them is going to be this one, and the other one is going to be AlphaGo. So it's good to compare and contrast the two things. So let's go back in history a little bit to 1997. So going back 20 years, and in 1997, an IBM computer called Deep Blue defeated Garry Kasparov, who at the time was the world chess champion. And Garry Kasparov was beaten in this match, and this was widely seen as a very significant landmark in artificial intelligence, a really major achievement. But it's interesting that even though we managed to build computers that could play chess at this level, that still everybody recognized that we hadn't really achieved human-level artificial intelligence. There was still an enormous number of things that computers couldn't do that humans can do, very ordinary, everyday things. Okay, so that was in 1997. So let's fast forward now, nearly 20 years. And in 2016, DeepMind's AlphaGo took on Korea's Lee Sedol, who is one of the top Go players in the world. And I think to everybody's surprise, Lee Sedol was beaten by AlphaGo by 4 games to 1. So this is another very significant achievement for artificial intelligence. And of course, many people thought that it would be a very long time before computers were able to compete at a professional level at a game like Go. So this was a great surprise. And then the following year, so AlphaGo also managed to defeat China's Keijie. And in this picture that we see, so at this event that took place in Wuzhen, there were many different types of Go matches. There was, of course, the match with Keijie, but there were also a number of other matches, and in one of them, there was a whole team of 5 Go masters that all took on AlphaGo and tried to act as a team and defeat AlphaGo. And even all 5 of these Go masters, top Go masters together, were unable to defeat AlphaGo. Now I want to say a little bit about how AlphaGo works and why it's such a remarkable achievement. Of course, one of the reasons it's a remarkable achievement is because Go is so very difficult. It's a very, very difficult game. It's much more complex than chess because the sheer number of board configurations you have in a 19 by 19 Go board is astronomically large, and it's astronomically larger than the number of board configurations you have in chess. Now, the number of board configurations that you have in chess is still very, very large, but it's not so large that a computer can't tackle the problem using sheer brute force of computation. And the way that Deep Blue tackled chess was by exploring the tree of possible moves. So given the current board configuration in chess, Deep Blue would look at the possible moves that it might take, and then the possible moves that its opponent might take after that, and then the possible moves that it might take after its opponent's move. And as you can imagine, this makes a sort of tree of possibilities. And this tree of possibilities fans out and is very, 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 very large. And in chess, it's very, very large. It's too large for humans to use a kind of brute force exploration of saying, what if I did this, and then they did that, and then I did this, and then they did that. We do that a little bit, but mainly human experts rely on their sort of intuition and their pattern recognition capabilities. Now, the way computers worked at chess was not by using that kind of intuition and pattern recognition capabilities, but rather was by using the sheer power of computing, the sheer speed of computing, was exploring this huge tree of possibilities. Now, it turns out that while humans can't tackle chess that way, but computers can, they can explore this tree of possibilities. But the tree of possibilities with Go is so much larger, so very much larger than chess. There's no way you can tackle Go using computers in that kind of brute force way. And that's why many people thought that we'd never be able to build computers that were professional level at Go. And even with 2017 computing power. And the point is, of course, that good human players use their intuitive understanding of the board and the board positions. And the clever thing is that DeepMind managed to replicate something of that intuitive pattern recognition capabilities. Okay, so I want to say a little bit more about how AlphaGo works. So like IBM's Deep Blue, AlphaGo does search this tree of possibilities, and it uses a method called Monte Carlo tree search. And what that means is that it makes sort of random forays into the search tree, and that's a very important aspect of the way AlphaGo works, is by doing this searching this tree. So that's kind of similar to the way that Deep Blue works. But what's different is that it uses neural networks in order to prune this tree. So this enormous tree of possibilities, it cuts out branches and limits its exploration by using neural networks. And this is the way it does it. So it uses deep learning, and it trains on a very large database of human expert games. And with this very large database of human expert games, 2 neural networks get trained. So one of the neural networks will take a board position and will tell you whether it's a good board position or a bad board position. So it evaluates the board position. And then another neural network will take a board position and will tell you what's the most likely next move that an expert player, a top player, would make. And using that information, it can cut down this huge tree of possibilities so that it's only looking at the moves that are potentially good moves because it's learned from this database of human expertise what is a good move. And it will only then continue the exploration if it knows it takes it to a board position that it knows is a good board position for AlphaGo. And it also uses a technique called reinforcement learning. So reinforcement learning is all about learning by trial and error, and it used self-play. So AlphaGo so its training was sort of boosted up even further from what it had achieved using the human expertise by training on, by playing against itself many, many times. Okay, so the really important thing in many ways about AlphaGo is that the underlying technology that it uses has wider application than just Go. It's very impressive what AlphaGo can do, and it uses reusable technology. But what about human-level AI? What about the kind of thing that we see in the science fiction films, in movies? Well, some authors, such as Ray Kurzweil, have predicted that a human-level artificial intelligence will be achieved by the 2020s. And the way that they work this out is by working out how many neurons there are in the human brain, working out how much computing power you'd need to simulate them, working out when we're going to get that kind of computing power. And when you extrapolate curves of how much computing power is increasing, such as this one here that shows the speed of the world's top 500 supercomputers, well, then it looks like we're going to have enough computing power to simulate all the neurons in a human brain at some point in the 2020s. Well, I think the argument is a lot more complicated than that. So I'm going to just tell you why. So I think that computing power alone is not enough to achieve human-level artificial intelligence, because we really need to know what to do with all of that computing power. And the question is, does the progress in AI software match the progress in the hardware? I think that there are still an awful lot of things that we need to do to get to human-level artificial intelligence. And I can sort of summarize that by thinking again about AlphaGo. So AlphaGo is certainly very clever. We know that it exhibits even a kind of creativity, and even its designers and Go masters don't fully understand what it's doing. However, like all specialized artificial intelligence, AlphaGo is actually, in many senses, not very clever, because all it can do is play Go. Whereas if we look at Lisa Doll, or KGA, the amazing thing about them is that not only can they play Go, but they can also do all of those everyday things that all of us can do, such as hold a conversation, or play with a child, or make a meal in a kitchen, and all the many, many ordinary everyday things that any human being can do. KGA can do those things, Lisa Doll can do those things, I can do those things, but AlphaGo can only play Go. AlphaGo doesn't even understand that there's a complex everyday world out there to deal with. So in order to achieve artificial general intelligence, in order to do that, then we require a number of other things. So in English, it's the 3 C's: creativity, common sense, and abstract concepts. So we need creativity, the ceaseless tendency to try out new possibilities, but that only works if the computers have common sense. So common sense is the ability to understand the consequences of everyday actions in the ordinary, everyday world. If you just think about all the many ordinary, everyday objects that are around you in, say, in your house or in the street, then we have a common sense understanding of the way they work and what will happen if we manipulate them, move them, put them inside each other, push them with each other. And we also have a common sense understanding of the social domain as well. So we don't yet know how to endow computers with that kind of capability. And we also don't know how to endow them with the ability to form the kinds of abstract concepts that humans can form and that help us to generalize in novel circumstances. So there's a number of things that we don't know how to do yet, and we need to be able to do those before we can achieve human-level artificial intelligence. And I think there's an unknown number of conceptual barriers before we get there. However, if we did get there, well, then we'd be getting towards this time that some people have called the technological singularity. And if we did get there, well, then I think there are certain very important things that we have to start to think about. And in fact, many of these, in the first set of bullet points here, are things that we have to think about anyway, even before we get to human-level artificial intelligence. So we have to think about the prospect of technological unemployment, and we have to think about our dependence on technology. So we don't want to become overly dependent on technology. And we also want to make sure that our technology, our AI, is safe and reliable. And if we ever manage to make human-level artificial intelligence, then these concerns will be much, much larger. However, if we do get these things right, then there is the possibility for very, very powerful and beneficial improvements to everybody's lives. And we end up starting, if computers and AI can enable a kind of utopia, then we have to ask ourselves a number of really deep and important questions, which are things like, what do we really want? What constitutes a good life? And what do we want as a species? And I think these kinds of issues and questions are things that transcend cultural and political differences. So they're things that we all need to be talking about. And my parting message that human-level AI may be a long time coming, but specialized AI technology is here now and is only going to get more powerful, and it's going to have a big impact. So thank you very much.